Yeah, thank you for attending my presentation. My name is Terence and in collaboration with Frederic, Leymarie and Mick Grierson at Goldsmiths and the Creative Computing Institute, we present our paper, Network Bending, Expressive Manipulation of Deep Generative Models. So network bending is a framework for the direct and expressive manipulation of the inner layers of generative models. And the key contributions of our framework is that we've implemented a suite of transformation layers that are implemented natively in PyTorch, which is a machine learning library. We present an unsupervised algorithm for clustering the features semantically. And we demonstrate our framework on StyleGAN2 and its use in expressive image generation. And finally, this is a novel approach for achieving active divergence, which I'm going to explain in a couple of slides. So just a quick background on generative models. So generative models are neural networks that learn to generate a given data distribution. So you give it training data and it learns to reproduce samples that look like the data. There's lots of approaches to doing this, and there's lots of architectures that you can use, but the ones that we're going to be using are generative adversarial networks, which refer to as GANs, and convolutional neural networks, which are commonly used in image analysis and image generation, which we'll refer to as CNNs. So there's been a lot of approaches for interacting with these models, and a lot of these approaches focus on navigating and understanding the latent space or manipulating the latent space. So we have approaches like space sheets and GAN space that are looking at how you navigate the latent space and giving you control over which direction in latent space you want to move in and explore. And then you have approaches like semantic latent manipulation, where you're producing an artifact by manipulating and operating on the latent vectors. There's some approaches that go further than this. So some approaches analyze and even manipulate the internal features. So a common approach, well, a famous approach is GAN dissection. So what they do here is they use ablation to turn features off and try and figure out what features are responsible for generating what by turning them off. And using this approach, we're able to find features, individual features that generate certain things. And then in the GAN pane framework, they then have a user interface which allows you to draw onto the activation maps of those features that they found with their analysis. So as you can see in the GIF here, you know, they're drawing doors on churches or trees in the sky. So we wanted to build on this work, but take it further. So with the GAN pane, it's quite limited. There's only a few features that you can work with. So it's more of a tech demo than necessarily a framework that, say, artists would want to use. And the other motivation is that high dimensional latent space is very difficult to interpret and control. So we wanted to give artists more meaningful control over what they're doing, but also give them flexibility and allow them to have a lot more control over what they're doing. So we want to give them control over the entire network hierarchy, and we want to maximize the flexibility in the way that the framework can be used. The other motivation for this work is for achieving active divergence. So generative models can only imitate what they've been trained on, and they're not very good at creating completely novel outcomes, which totally diverge from the training data. And so methods that do try and actively diverge from the training data have been referred to as active divergence in this paper from Sebastian Burns and Simon Colton from ICCC last year. And with our network bending, we want to create a new method for doing this. So StyleGAN2, which is the GAN that we're going to be working with, is a CNN-based GAN. It's the state of the art in unconditional image generation. It can produce very high resolution and photorealistic images, and it's widely used by artists and hobbyists. People train their own models using platforms like Runway ML and Google Colab. And so we want to demonstrate our framework on this network because of its prevalence used by the kind of artistic community and research community as well. So inside StyleGAN, we have these convolutional blocks on the diagram on the left. It's not too important to understand all the details, but basically we have these blocks which do the kind of upsampling and generation, and they take a style vector and a noise vector, and then you have a convolutional filter, but you also have a normalization layer. after the normalization layer, you have these activation maps, and as you can see them on the right, these are the activation maps inside the model. So each convolutional layer has lots of these features or filters, and in the higher layers, they're very low resolution, and they become bigger in resolution at the lower layers. And they're activations on a tensor, but you can interpret them as one channel images. And so what we're going to be doing is we're going to be manipulating directly onto these activation maps. So here's an overview of the network bending framework. So we're taking pre-trained generative models, and we're not making any changes to the weights or the network architecture, except the fact that we're inserting these new layers that perform deterministic transformations to the activation maps. And these transformations are applied to each activation map individually, but when they're done in tandem, you get results that end up affecting the whole image. So in this example, we've selected all the features that generate eyes, and then we scale them down by 50%. And you can see that transformation happening here on the activation maps, and then they've been scaled down, and then the rest of the inference is enrolled in the generator, and then in the result here, we can see the eyes have been shrunk down compared to the unmodified result. So we have three different categories of transformation layers. So the first is numerical. So these are just applying simple numerical filters to each individual pixel or activation node. And so we have ablation, which is basically multiplying by 0. So that's turning it off. We've got scalar multiplication, which can be multiplied by any real number. Inversion, so we just do 1 minus the activation. And then a binary threshold, which is just if it's above a certain threshold, we make it 1. If it's below a certain threshold, we make it 0. It's also referred to as posterization. We also have affine transformations. So these are implemented in custom C++ operators in OpenCV. And these, we have translation. So that can be done in the X or the Y direction. We've got scaling, which is done uniformly in X and Y. Rotation, and then reflection, which can be done horizontally and vertically. But in this case, this is horizontal. And then we also have morphological transformations. Again, these are OpenCV C++ custom operators that are then integrated into PyTorch. And we have erosion and dilation, which are just done with circular structuring kernels with a pixel radius of 2. This diagram shows the variety of outcomes that you get by applying the same transformation layer in different layers of the model. And this just kind of shows like the flexibility and the different outcomes that you can get by applying the same transformations at different points. So with, for instance, this binary threshold, if we apply binary threshold in higher layers of the model, we get these really horrifying results, but in the lower layers, we get these quite painterly results. And so we, like I said, we wanted to maximize the flexibility and exploring creative outcomes with our framework. There are 3 different ways of applying the transformation layers. So you can apply them to all the features in a layer. So in this case, we're scaling all of the features in the layer down, and then we get this kind of head floating in space. They can also be done stochastically. So you can say, I want to apply this filter to n percentage of features in a layer. Or they can be done with a predefined cluster, which we will explain how we do this in a second. So this is the next part of our framework, which is how we cluster features. And the guiding principle that we took on this is that features with similar activation maps that appeared similarly will have similar functions. So for instance, all of these activation maps have these 2 blobs about 2/3 of the way up the image. And if I was to hazard a guess, I would say they would all generate eyes. And so our guiding principle is that if we group them together based on what they look like, then hopefully that corresponds to them also, when we manipulate them, the same features get manipulated in the same fashion. So our approach to doing this is that we train a CNN for each layer. We train a CNN classifier, and our approach is using the softmax classification feature learning technique. And so this basically means you train a softmax classifier. So we just try classifying what each feature is based on its activation map. And then we then use the feature vector prior to classification. We use that as a feature vector for metric learning. So we're just getting distances of how similar or dissimilar two examples are. But what we do is we add a bottleneck prior to classification to reduce the dimensionality of that feature vector. So we have a bottleneck of 10, a vector of 10, prior to, say 500 classification. So this gives us a really compressed representation. And we use a shuffle-net architecture, which is just a very efficient CNN architecture. And we have adaptive depth because different layers of the GANs have different resolution activation maps. So then we perform k-means clustering. So we get a mean feature vector for each sample. So in this case, we generated 1,000 samples, and then we got mean feature vectors that represented each convolutional filter. And then we perform k-means clustering on these feature vectors for each layer, and we just have a predefined number of clusters for each layer. And then once we calculate the clusters, we save them to a dictionary for later use. So these are some of the results from our clustering. So basically, in the upper layers, say on B here, all of the features that generate the face have been grouped together. And if we invert them, the face completely disappears, but we still have the background and we have the hair. And then in the middle layers, we find sets of features that generate eyes. So here we can turn them off, or nose. Here we can enlarge the nose. And then in the lower layers, we then have features that generate groups of features that generate textures, a cluster of features that sort of represents facial highlights. And in the very low layers, we have more basic things like brightness and contrast. And this is a comparison, an ablation comparison. So basically, the GAN dissection approach, which uses ablation for trying to understand the features. In this example, if we ablate this cluster of features in this church's model, this roof behind these trees disappears, but it's you might not notice it. It might be quite hard to tell. Whereas when we multiply it by a factor of 5, suddenly it becomes a lot more prominent, and this roof gets generated instead of the trees. And we also get another section of gable roof on the other side of the church. So another thing that we want to advance with this is that having all of these different transforms allows us to, gives us more possibility and better understanding of what the models are doing from a perspective of interpretability. So this is an overview of our pipeline. So we have the analysis phase where we train classifiers and we would calculate the clusters. And then during inference, we have a config file where we load that, we load the and then we perform inference. And using our plugin architecture, we're dynamically inserting these transformation layers as inference is enrolled. And then we return a generated output. I'm going to skip this for time. So one of the things that excites me personally, and I think is a really interesting avenue to explore with this work, is when you train these transformations, you get really, really unexpected results and really interesting results. And so it's very easy once you start to use more than one transformation in different layers to get really out there results. And I think with our goal of making expressive interfaces, we want that opportunity for people to explore and to also kind of explore new outcomes, but also find a kind of style and a sort of something that works for them, which they can use to express their own artistic outcomes. This is a case study of how we used stochastic layers. So stochastic layers are where they applied randomly. And so in this, you can see, so in this, so I was commissioned to make a series of EP artworks for the band 0171. And so what we did here is that we wanted to use this network bending code that I'd made, and the band gave us some photographs of them. Initially, we used different pictures, but because it's a pop music band, they wanted something colorful. So eventually they took photos in front of these colorful paintings. So this is one of the band members, Joe. This is the original photo of him. This is a projection into StyleGAN latent space. And then what I was doing was I was experimenting with lots of different configurations of training these stochastic layers. And I would try out lots of different things, find ones that produce interesting results, send them to the band. They would tell me which ones they liked, which ones they didn't like, what they wanted more of, what they wanted less of, and then I would go back and then I would try out more stochastic things, generate more results. And there was this kind of back and forth. And eventually I found two kind of configs that produces really good results that the band really liked. And I generated a lot of images. So I generated 500 images using these stochastic layers, and are all different, slightly different variations, all using the same latent vector here. And eventually these were the 5 EP artworks that the band chose. So completely unmodified. These were, they used each one for each single. And these 3 on the left here were using one config, and these 2 were using a different config. But I think this kind of goes to show a different way. So instead of just working on generating one artifact, we're generating lots of them, and we're exploring what one config can do to generate lots of results that all have a shared common aesthetic. I've also used this network bending in a series of my own artworks called Teratome. And again, you know, it's using these faces models, but it's applying these kind of filters in the higher layers of the model, and then exploring that and producing kind of these very photorealistic but very distorted images. So the original paper of this network bending went on archive last summer. And so there were actually 2 papers that were based on my work at the NeurIPS creativity workshop last year. So the first one is this network bending neural vocoders, which was done by my colleagues at CCI and Goldsmiths, Louis McCallum and Matthew Yeking, where they applied the same network bending framework to audio generation using Google Magenta's DDSP. And network bending was also applied in this paper, Audio Active Latent Interpolation, where using audio signals for interpolating the feature vector, interpolating the latent vector, and generating visuals in response to that. But in addition to sort of operating on the latent vector, they're also using network bending and using features from the music in real time to manipulate the generated results. Sorry. So in future work, one of the things we'd like to do is build and test an interface. So at the moment, I skipped one of the slides, but it's currently configured using YAML configs, and I think that's not particularly user-friendly for artists. So obviously, I think building a user interface is going to be key to better understanding and making this work more accessible, but also trying to then test out our claims about it being an expressive framework. We also want to extend it into other domains. So it has already been extended into audio, but I think there's more scope for extending it into more kinds of audio and also other kinds of models. So I think recurrent neural networks and autoregressive models and transformers all are different architectures that have different kinds of properties. And I think applying network bending into different kinds of models instead of the feed-forward models like StyleGAN, I think would produce some really interesting results. So that's something I'd like to do in the future. And so just to conclude in a bit of a recap, in this presentation, we've presented our network bending framework and we've demonstrated it on images using StyleGAN2. We've implemented a suite of transformation layers natively in the PyTorch machine learning library, which the GAN is also running, so for efficiency. We've got transformations that are inserted and applied dynamically using our plugin architecture. We've presented a clustering algorithm which is unsupervised and capable of finding semantically meaningful sets of features across the entire network hierarchy, which is a significant advance on the GAN dissection framework. We've demonstrated the potential in producing expressive images, and we've also presented a new method for achieving active divergence from the training data. So thank you for listening, and I'm happy to take any questions.
Thank you, Terence, for your presentation. In chat, you'll find already a question by Simon. If you
okay, all right, hold
read it.
Wait, sorry.
If you prefer, you can stop sharing the screen.
Yeah, okay.
I believe it will be easier.
I've lost.
Don't worry.
I've lost Zoom. Oh, here it is. Okay.
Oh, okay.
Yeah, chat. Okay. We've mentioned your work in our computational creativity lecture. Similar results. Others would require too much photoshopping. Would you say that the manipulation could become standard, or are there characteristics of the manipulations that would be really tricky? I think, yeah, so I mean, this is another thing that we wanted to do was achieve active divergence, but also it's a new way of producing images, and I think the images that we produce would be really hard to produce using any other technique, so that was another motivation. I'm a bit confused by this question. Will active divergence become boring graphics? I mean, maybe that's a success. Maybe becoming boring graphics is a sign of success. I don't know. Maybe that's the aim.
Yeah, sorry, Terry, I didn't phrase the question very well. It's not a question of, well, I presented this work to the students on the course, and I tried to get across the fact that some of them you're recreating standard graphics manipulations like inverse.
Yeah.
But other ones, you certainly aren't. I mean, it'd be very difficult to imagine doing them with Photoshop. And I just wondered whether you had any kind of handle on the manipulations which do normal transforms and ones which don't. Has anything come up in that respect?
Yeah, well, I mean, I think also it's kind of the, things like inversion. I've given examples in the presentation which are very clear in terms of what they're doing, because I've tried to pick samples that are very obviously reference what inversion would look like in a standard when you apply it to a standard image. But actually, when you apply inversion to sort of higher layers, then you get very different results. But it wouldn't be hard. It'd be quite hard. It wouldn't make a lot of sense if I was giving you the examples which were kind of unexpected.
Mm-hmm.
If that makes sense. So actually, I think something like inversion can produce really, really unexpected results when you're experimenting with this framework.
Okay, cool. Thanks.
Yeah.
Okay, Terence, thank you for your presentation again. So I believe, yeah, we are on time. I believe we can move on to the next presentation.